Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about Fermi energy, Fermi-Dirac distribution function, and position of Fermi level in intrinsic and extrinsic semiconductors. In this lecture video, I will discuss about p-n junction. So let's get started. The content of this lecture video is as follows. First of all, I will discuss about p-n junction, followed by p-n junction diode and its working mechanism with the help of IV characteristics curve. Further, I will discuss about the expression for barrier potential and ideal diode equation. A p-n junction is a boundary or interface between two types of semiconductor materials, p-type and n-type, inside a single crystal of semiconductor. The P stands for positive, side contains an excess of holes, while N stands for negative, side contains an excess of electrons in the outer shell of the electrically neutral atoms which are there. This allows electrical current to pass through the junction only in one direction. The p-n junction is created by doping, for example, by ion implantation, diffusion of dopants, or by epitaxy, that is growing a layer of crystal doped with one type of dopant on the top of a layer of crystal doped with another type of dopant. If two separate pieces of material were used, this would introduce a grain boundary between the semiconductors that would severely inhibit its utility by scattering the electrons and holes. The detail about this we will discuss in last unit, that is physics of nanoparticles. p-n junctions are elementary building blocks of semiconductor electronic devices such as diodes, transistors, solar cells, LEDs, and integrated circuits. They are the active sites where the electronic action of the device takes place. For example, a common type of transistor, the bipolar junction transistor, consists of two p-n junctions in series in the form of NPN or PNP, while a diode can be made from a single p-n junction. A Schottky junction is a special case of p-n junction where metal serves the role of the n-type semiconductors. As we know, if we use different semiconductor materials to make a p-n junction, there will be a grain boundary that would inhibit the movement of electrons from one side to the other by scattering the electrons and holes, and thus we use the process of doping. We will understand the process of doping with the help of one example. Let us consider a thin p-type silicon semiconductor sheet. If we add a small amount of pentavalent impurity to this, a part of the p-type silicon will get converted to n-type silicon. This sheet will now contain the both p-type region and n-type region and a junction between these two regions which is called p-n junction. The process that follow after the formation of p-n junction are of two types, diffusion and drift. So this diagram shows the p-n junction. Here the symbol for p-n junction is shown, in which the triangle corresponds to the p side which is connected to the anode, whereas another opposite side is connected to the cathode. Now let's see the formation of p-n junction. Now consider p-type material combined with n-type material. At the interface, a junction is formed which is called as p-n junction, which is we have already discussed before. As we know, there is a difference in the concentration of holes and concentrations of electrons at the two sides of a junction. The holes from the p side diffuse to the n side and the electrons from the n side diffuse to the p side. This gives rise to a diffusion current across the junction. When an electron diffuses from the n side to the p side, an ionized donor is left behind on the n side which is immobile. As the process goes on, a layer of positive charge is developed on the N side of the junction. Similarly, when a hole goes from the P side to the N side, an ionized acceptor is left behind in the P side, resulting in the formation of a layer of negative charges in the P side of the junction. This region of positive charge and negative charge on either side of the junction is termed as depletion region. And the potential across this depletion region is called as a potential barrier. Now let's see the biasing conditions for the PN junction diode. There are two operating regions in the PN junction diode, that is P-type and N-type. There are three biasing conditions for PN junction diode, and this is based on the voltage applied. First of all, zero bias. There is no external voltage applied to the PN junction diode. Second one is forward bias. The positive terminal of the voltage potential is connected to the P-type, whereas the negative terminal is connected to the N-type. Then we can say that PN junction is forward biased. Third one is reverse bias. The negative terminal of the voltage potential is connected to the P-type and the positive is connected to the N-type. In this case, PN junction diode is in reverse bias condition. Now let's see all these biasing conditions in detail one by one. First of all, zero biased or unbiased. In zero biased condition, there is no external voltage applied to the PN junction diode. When P and N semiconductors combine at the interface, depletion region formed. Due to depletion region, positive space charge region on the either side of the junction, an electric field direction from a positive charge towards the negative charge is developed. Due to this electric field, an electron on the P side of the junction moves to the N side of the junction. This motion termed as drift. Here we see that the direction of drift current is opposite to that of the diffusion current as shown in this diagram. Now let's see the non-equilibrium state of PN junction in unbiased condition. A PN junction diode is constructed by joining P and N type semiconductors. When P and N type semiconductors are in isolated from each other, they are said to be in non-equilibrium state. Fermi level EF of N-type semiconductor is located close to the bottom of the conduction band at ECN, and the Fermi level EF of P-type semiconductor is located close to the top of the valence band at ECP. This is shown in this diagram. Now let's see PN junction at thermal equilibrium. The formation of depletion region is when the two semiconductors are joined, the electrons from the N side are diffused to the P region and they form a layer of negative charge on the P side. Thus, the Fermi level of N region decreases. The electrons leaving N side enters into the P region and the holes from P side diffuse to N side. Thus, the Fermi level of P region increases. So at equilibrium condition, when the equilibrium achieved, the movement of electrons and holes across the junction stops and a depletion region is formed. The band edges in the two regions shift themselves so that Fermi levels are properly aligned and attained equilibrium. The Fermi level in N region shifts down by an energy EV0, whereas Fermi level in P region shifts upward by the same energy EV0, where V0 is the potential barrier across the junction. After equilibrium is attained, the majority electrons from N region face the potential barrier across the junction. Thus, they cannot cross the junction and no current flows. Now let's see the PN junction diode in forward biased mode. When P-type is connected to the positive terminal of the battery and the N-type to the negative terminal, then the PN junction is said to be forward biased. When the PN junction is forward biased, the built-in electric field at the PN junction and the applied electric field are in opposite directions. When both the electric fields add up, the resultant electric field has a magnitude lesser than the built-in electric field. This results in a less resistive and thinner depletion layer or the region. The depletion region's resistance becomes negligible when the applied voltage is large. In silicon, at the voltage of 0.6 volt, the resistance of the depletion region becomes completely negligible and the current flows across it. This phenomena is demonstrated in this diagram. Now let's see the band diagram for forward biased mode. An external potential difference, capital V, is applied to diode in forward bias. This voltage should be greater than the potential barrier of V0. Now electrons from the source are added to N region, hence potential in N region rises by E into V0 minus V. The Fermi level of P region goes down. Electrons in N region now face a lower potential barrier. The width of potential barrier is reduced. Hence electrons from N region across the junction easily to enter into P region and electrons flow increases. This constitutes forward bias current. This current increases with increase in forward biased. So in this diagram, E into V0 minus V, here E is the charge on charge carriers, V0 is the initial potential difference, and V is a applied potential difference through the battery. Now let's see the PN junction diode in reverse biased mode. When the P-type is connected to the negative terminal of the battery and N-type is connected to the positive side of the battery, then the PN junction is said to be reverse biased. In this case, the built-in electric field and the applied electric field are in the same direction. When the two fields are added, the resultant electric field is in the same direction as the built-in electric field, creating a more resistive, thicker depletion region. The depletion region becomes more resistive and thicker if the applied voltage becomes larger. Now let's see the band diagram for reverse biased mode. An external potential difference, capital V, is applied to diode in reverse bias. Due to this, electrons are removed from N region. Hence potential in N region decreases by E into V0 plus V. Electrons enter into P region and hence potential in this region rises. Electrons in N region now face a higher potential barrier. The width of potential barrier is increased. Hence electrons from N region cannot cross the junction easily to enter into P region and the electron flow decreases. However, small leakage current flows through the junction, which constitutes reverse bias current. Now let's see IV characteristics of PN junction diode. Before that, try to understand how does electron flow in PN junction diode. The flow of electrons from the N side towards the P side of the junction takes place when there is an increase in the voltage. Similarly, the flow of holes from the P side towards the N side of the junction takes place along with the increase in the voltage. This results in the concentration gradient between both sides of the terminals. Because of the formation of the concentration gradient, there will be a flow of charge carriers from higher concentration regions to lower concentration regions. The movement of charge carriers inside the PN junction is the region behind the current flow in the circuit. In IV characteristics of PN junction diode is a curve between the voltage and the current through the diode current. Voltage is taken along x-axis while the current is taken along the y-axis as shown in this diagram. The graph shown in the diagram is the IV characteristics curve of the PN junction diode. With the help of the curve, we can understand that there are three regions in which the diode works, and that regions are zero bias, forward bias and reverse bias. All these three regions we have already discussed before. When the PN junction diode is under zero bias condition, there is no external voltage applied, and this means that the potential barrier at the junction does not allow the flow of the current. When the p-n junction diode is under forward bias condition, the p-type is connected to the positive terminal while the n-type is connected to the negative terminal of the external voltage. When the diode is arranged in this manner, there is a reduction in the potential barrier. For silicon diode, when the voltage is 0.7 volt, and for the germanium diodes, when the voltage is 0.3 volt, the potential barriers decreases and there is a flow of current. When the diode is forward biased, the current increases slowly and the curve obtained is non-linear as the voltage applied to the diode is overcoming the potential barrier. Once the potential barrier is overcome by the diode behaves normal and the curve rises sharply as the external voltage increases and the curve so obtained is linear. When the p-n junction diode is under negative bias condition, the p-type is connected to the negative terminal while the n-type is connected to the positive terminal of the external voltage. This results in an increase in potential barrier. Reverse saturation current flows in the beginning as minority carriers are present in the junction. When the applied voltage is increased, the minority charges will have increased kinetic energy which affects the majority charges. This is the stage when the diode breaks down. This may also destroy the diode, or this voltage is called as the breakdown voltage. Now let's see the expression for barrier potential. The internal potential barrier V0 for a diode can be calculated from the electron concentrations in p and n regions. The Fermi function f of e gives the probability that the energy state will be occupied by the electron at temperature T, which is given by f of e is equal to 1 upon 1 plus exponential of e minus ef upon kt. Let's say this is equation number 1. This equation we have already discussed before. In this equation, the parameters f of e is a Fermi function, capital E is the energy of given state, E of f is a Fermi energy, capital T is the temperature in Kelvin for the available state, small k is the Boltzmann constant whose value is 1.38065003 times 10 raised to minus 23 joules per Kelvin. The band diagram given here gives us the complete explanation about how the charge carriers behaves when the p-n junction diode forms and under the different conditions which we have already discussed before. Using Fermi function, the probability of occupation of electrons small n subscript small n out of average concentration of electrons in conduction band, which is capital N subscript small c, in Fermi level capital E subscript f is given by n is equal to nc divided by 1 plus exponential of Eg minus Ef upon kT. Let's say this is equation number 2. In this equation, Nn is the electron concentration in the conduction band on the n side, Np is the whole concentration in the conduction band on the n side, capital N subscript C is the average concentration of electrons in conduction band of p and n side, Eg is the band gap energy, Af is the Fermi energy, small k is the Boltzmann constant, and capital T is the absolute temperature in Kelvin. When the number of particles is very small compared to the available energy levels, the probability of an energy state being occupied by more than one electron is small. In this situation, Eg minus Ef is very much greater than 3 kT. Due to this, now we have 1 plus exponential of Eg minus Ef upon kT is nearly equal to exponential of Eg minus Ef upon kT. Thus, Nn is equal to Nc upon exponential of Eg minus Ef upon kT. Therefore, by simplifying this equation, Nn is equal to Nc into exponential of minus Eg minus Ef upon kT. It can be written as Nn is equal to Nc into exponential of minus Eg minus Ef upon kT. Let's say this is equation number 3. Due to the barrier potential capital V naught, the band gap energy on P region increases by Eg plus EV naught. The electron concentration on P side can be written as Np is equal to Nc into exponential of minus Eg plus EV naught minus EF divided by Kt. Let's say this is equation number 4. Dividing equation number 3 and equation number 4, we get Nn upon Np is equal to Nc into exponential of minus Eg minus Ef upon Kt divided by Nc into exponential of minus Eg plus Ev naught minus Ef upon Kt. Therefore, Nn upon Np is equal to exponential of Ev naught upon Kt. Let's say this is equation number 5. Taking logarithm on both sides, we can write ln of Nn upon Np is equal to Ev naught upon Kt. Therefore, V naught is equal to Kt upon E ln of Nn upon Np. Let's say this is equation number 6. If capital P subscript P is a concentration of holes in P region, above equation can be written as capital V naught is equal to Kt upon E ln of Nn into Pp divided by Np Pp. Let's say this is equation number 7. Now let's consider capital N subscript capital D is the concentration of donor atoms and capital N subscript capital A is the concentration of acceptor atoms. Then at room temperature, all the impurities are ionized. Hence, we can write small nn is equal to capital ND and Pp is equal to capital NA and NnPP is equal to Ni square. I stands for the intrinsic. Hence equation number 7 can be written as capital V naught is equal to Kt upon E ln of Nd into Na upon Ni square. Let's say this is equation number 8. The factor Kt upon E is of the dimension of the voltage and is denoted by capital V subscript capital T. Hence above equation can be written as capital V naught is equal to capital V subscript capital T ln of capital N subscript capital D into capital N subscript capital A divided by Ni square. Let's say this is equation number 9. Thus, barrier potential in a junction diode depends on the equilibrium concentration of the impurities in P and N regions and does not depend on the charge density in the depletion region. Equation number 9 is nothing but the expression for barrier potential for the p-n junction diode. Now let's see one example which is based on equation number 9. Calculate the potential barrier for a germanium p-n junction diode at room temperature, that is 27 degrees Celsius, if both P and N regions are doped equally and to the extent of 1 atom per 10 raised to 6 germanium atoms. Given parameters, that is concentration of germanium atoms is equal to 2 into 10 raised to 19 per meter cube. Concentration, that is the carrier concentration of intrinsic germanium is 4.4 into 10 raised to 28 atoms per meter cube. And Boltzmann constant is equal to 1.38 into 10 raised to minus 23 meter square kilogram per second square Kelvin. Therefore, solution for this problem is as follows. Temperature capital T is equal to 27 degrees Celsius. Convert it into degree Kelvin, that is 300 Kelvin. As intrinsic germanium is doped equally with 1 atom per 10 raised to 6 germanium atoms, then the concentration of donor and acceptor atoms can be calculated as follows. Na is equal to Nd, that is equal to 4.4 into 10 raised to 28 divided by 10 raised to 6, that is equal to 4.4 into 10 raised to 22 atoms per meter cube. Therefore, we have the equation capital V naught is equal to KT upon E ln ND NA upon NI square, which is equation number 9. Therefore, capital V naught is equal to the Boltzmann constant 1.38 into 10 raised to minus 23 into temperature 300 Kelvin divided by charge on electron 1.602 into 10 raised to minus 19 into ln of 4.4 into 10 raised to 22 square divided by Ni square is a 2.4 into 10 raised to 19 square. Therefore, after calculating this, we get final value 0.42 volt. Therefore, the potential barrier for a germanium is 0.42 volt. So this is the solution of this problem. Now let's see the ideal diode equation. The current flow through the diode is shown in this diagram. This diagram we have already seen before. The ideal diode equation is an equation that represents current flow through an ideal p-n junction. When the diode is unbiased diode condition, the current due to diffusion can be calculated. When p and n regions are brought together due to concentration difference, holes in p region diffuse to n region and electrons in n region are diffused to p region. Therefore, by using some special notations, we can calculate the ideal diode equation as follows. Let J, capital J E df UB is the electron diffusion current density of unbiased diode. So in this case, J is a current density, E stands for electrons, df stands for diffusion, and UB stands for unbiased. In second notation, capital JH of df UB, which is the whole diffusion current density of unbiased diode. So in this case, capital J is the current density, H is for the whole, D for diffusion, and UB for unbiased diode. In second case, the current due to drift, due to potential barrier, electrons reaching the edge of the junction on P side are accelerated by electric field into N region, and similarly, holes reaching the edge of the junction on N side are accelerated into P region. Therefore, by using special notations, let capital J E of dr UB, which stands for electron drift current density of unbiased diode. Similarly, JH of dr UB, which stands for whole drift current density of unbiased diode. Therefore, for forward biased diode, when the diode is forward biased with potential VF, capital V subscript capital F, this is the forward potential. The potential barrier is lowered by an amount of energy EVF, and the probability of a majority carrier crossing the junction and the diffusion current density is increased by a factor of exponential of EVF upon KT. Therefore, electron diffusion current density in forward bias, we can write JE df of FB, FB stands for forward bias, is equal to JE of df UB times exponential of EVF upon KT. Let's say this is equation number 1. And whole diffusion current density in forward bias is JH of dfFB is equal to JH of dfUB into exponential of EVF upon KT. Let's say this is equation number 2. Now under equilibrium, whole diffusion current density is equal to whole drift current density. Therefore, JF of dfFB is equal to JF of dfUB into exponential of EVF upon KT is equal to JH of drUB into exponential of EVF upon KT. Let's say this is equation number 3. Electron diffusion current density is equal to electron drift current density. Therefore, we can write JE of dfFB is equal to JE of dfUB into exponential of EVF upon KT is equal to Je of drUB into exponential of EVF upon KT. Let's say this is equation number 4. The drift current density components have not changed and have the same magnitude as in equilibrium case. Therefore, let Je net is equal to net electron current density of unbiased diode and JH net is equal to net hole current density of unbiased diode. Therefore, the net hole current density across the forward bias junction is JH net is equal to JH of DFFB minus JH of DRUB. Let's say this is equation number 5. Therefore, we can write JH net is equal to JH of DRUB into exponential of EVF upon KT minus JH of DRUB. Therefore, JH net is equal to JH of DRUB into exponential of EVF upon KT minus 1. Let's say this is equation number 6. Similarly, Je net is equal to Je of drUB into exponential of EVF upon KT minus 1. Let's say this is equation number 7. Now let J total is equal to total current density across the forward bias junction. Therefore, we can write J total is equal to JH net plus Je net. Let's say this is equation number 8. Therefore, J total is equal to JH of drUB into exponential of EVF upon KT minus 1 plus Je of drUB into exponential of EVF upon KT minus 1. So this equation we can write J total is equal to exponential of EVF upon KT minus 1 into Je of drUB into JH of drUB. Let's say this is equation number 9. Let J naught is equal to Je of drUB into JH of drUB. Therefore, J total is equal to J naught of exponential of EVF upon KT minus 1. Let's say this is equation number 10. As we know that current density is nothing but current upon the area, therefore J is equal to I upon A is a current density. Therefore, equation 10 can be written as in this form: I is equal to I naught into exponential of EVF upon KT minus 1 bracket complete. So this is equation number 11. In this equation, I naught is nothing but J naught upon A. The above equation is called as a diode equation, where capital V denotes the voltage, which is V is equal to VF is a forward bias, and V is equal to minus VR for reverse biased, and I naught denotes the reverse saturation current. Diode current equation expresses the relation between the current flowing through the diode as a function of the voltage applied across it. Now let's see one problem which is based on the diode equation. Current flowing in a PN junction is 0.2 microampere at room temperature when a large reverse bias voltage is applied. Calculate the current when a forward bias of 0.1 volt is applied. The solution for this problem is as follows. We have the diode equation, which is I is equal to I naught exponential of EVF upon KT minus 1. Here the given parameters are I naught is equal to 0.2 microampere, forward bias voltage is 0.1 volt, and we have the Boltzmann constant, that is 8.617333.262 into 10 raised to minus 5 electron volt per Kelvin. So simply by putting these values in this equation, so solving this, we have current I is equal to 9.2 microampere. So this is the solution of this problem. Now let's see some applications of PN junction diode. PN junction diode can be used as a photodiode, as the diode is sensitive to the light when the configuration of the diode is reverse biased. It can be used as a solar cell. When the diode is forward biased, it can be used in LED, that is light emitting diode applications. It is used as rectifiers in many electric circuits and as a voltage controller oscillator in varactors. This is all about PN junction. In next lecture video, I will discuss about applications of PN junction. As an example, we will study solar cells principle, construction and working in detail. So please don't miss my next lecture video. Thank you. Video in the description. The link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.